I originally pitched to create a top-down space shooter where you defend against scavenger ships. These ships would be able to fly and attack. To defend, the player would have to destroy these ships, and survive against an increasing number of them. Although the outcome wasn't my exact plan, I kept most of it intact and believed that with a bit more time I could have achieved my original goals. The game is handled with the state machine, which I start with in the main function. Each state calls their respective scripts when active. I change its state during certain events, such as pressing buttons on the menus or getting hit by the enemy. My menus operate very similarly. First I make a constructor class to pass through the renderer and the window from the state machine. In the initialize function I set up any textures I'm using and the background music. Then for the menu to run, I set the isRunningBall to true. The update function calls two other functions, process input, which is used to handle the button presses, and the render function, which copies the textures to the scene and sends it to the renderer from the state machine. The only variation between the menus is the high score display in the end menu. This high score is encrypted using XOR encryption. At the end of the game, this high score is encrypted and then saved to a text file. Then in the end menu, I use a decryption function to get the actual score that should be displayed. As the high score is saved to a text file, it is saved even when the game is completely closed. A constructor is used for the game loop, so the window and hide can be passed through from the state manager. In the initialize function, I set up various other classes to use, as the game loop acts for a hub for functions of those classes to be run through. Moving on to the update function. This is where I update each of the class's respective update functions, and call game loops input and render functions. I'm also using an intentional delay here to keep the game running at 60 frames. In the input function, I'm checking for any changes in the game's state. I couldn't figure out why the game state wouldn't originally update outside this function, but I did find a fix for it. I'm also updating the enemy's A-star movement here, as I class it as a type of input. It also just helps separate things. The render function calls each class's render function and sends it to the renderer in State Manager. Next, cleanup is called, which frees up any memory of each of the classes. Finally, I have some quickly put together functions which send the game state to the handler and updates the tile map based on the player's position. The latter was quickly put together just for some more variety in gameplay. The tile map is manually created using this tile sheet. The tile map is loaded and stored in binary in an external text file. I manually select each tile to use and tell the draw function which one to place where, depending on the values stored in the binary file. The tile map can also be edited during the game. This is used mainly to change tiles out for power-ups. Bullets are pre-allocated so object pooling can be used. This helps with memory management. The bullets are deactivated once they travel too far from the player. Once a bullet is shot, a sound is played. This is managed by a sound player class. The bullets can also be shot at any rotation, which is a requirement as my player can rotate. Bullets can also be shot quicker by calling this function. It is mainly used for the power-up feature. Here I manage spawning asteroids from the side of the screen. They are randomly spawned. There is a check for screen bounds, which removes them if they leave the visible area. Each asteroid and bullet from the bullet class is given an SDL rect. This is utilised in intersects rect. When this event happens, both are removed and a particle effect is triggered at the asteroid location. The particles are handled by a particle class. For my moving enemies, I'm utilising an A-star algorithm, as it's an efficient way to find a path to a destination. In this case, my player, which is set in the enemy's movement class. The algorithm increases its frequency over time, which makes the game more difficult. I ran multiple tests for the update and initialization functions. The averages can be found in the readme. The update functions ran around 20 milliseconds, which is good considering the amount of stuff the game has. I also ran profiling tests within Visual Studio to get CPU usage. From these tests I found that CPU usage on the menus was abnormally high compared to the game. I wasn't able to figure out why, but this is something I'm going to look into next time. It doesn't cause any noticeable issues within the game though. I created this basic unified modeling language layout of how the project manages its functions and how it runs. I'm happy with what I was able to achieve with this project in the given time frame. However, I think I could have done a better job with profiling and keeping an eye on CPU usage in particular. For example, the menus use an abnormal amount of the CPU, and I'm not sure why, because I didn't leave myself with enough time to profile and diagnose the issue. The menus were a last minute addition, leading to them not being well implemented into the project. While functional, it's still a bit janky to use in the code. When creating a project like this in the future, I would start with the design phase first and get an idea of how the game systems would function before moving on to programming the game. Overall, though I feel I achieved what I set out to in the beginning phase of the project, with a little more time management and consideration of game flow and systems, I believe it would have panned out better than it did. However, I'm still happy with what I was able to achieve.